Today, we are going to talk about two of the most extraordinary ideas the human mind has ever produced. Ideas that reach into the very structure of the universe and ask whether the rules can be bent or whether the rules themselves might carry us forward if we simply learn to listen to them. Somewhere out there, 4 light years away, which sounds almost close until you understand what it means, there's a small red star called Proxima Centauri. Orbiting it is a rocky world, roughly the size of our own, sitting in what astronomers call the habitable zone, a place where liquid water might exist, where the temperatures might, in some latitudes, feel familiar to a human body. We have never been there. We have never sent anything there. The fastest spacecraft humanity has ever launched, Voyager 1, now drifting silently beyond our solar system after 47 years of travel, would take approximately 73,000 years to cover that distance. Civilizations would rise and fall. Languages would be born and die, and the probe would still be traveling. And so, for a long time, we told ourselves that the stars were simply too far, that interstellar travel was a domain of science fiction, a beautiful dream, but not a serious scientific pursuit. That time is over. In the last 3 decades, 2 technologies have emerged from the equations, not from imagination, but from peer-reviewed physics, that represent genuine, if deeply challenging, candidates for crossing interstellar space. The first is older than the space age, quietly patient and powered by the most abundant energy source in the universe, light itself. The second is so audacious, so geometrically strange, that it sounds like something a civilization 10,000 years more advanced than ours might build. And yet it was derived from equations we already have. One asks the universe to carry us. The other asks to reshape the universe around us. This is the story of both. And somewhere in the telling, you may find something that surprises you, not just about physics or engineering or the limits of the possible, but about what kind of species we are and what kind we might someday become. Let us begin with a number, 4.24. That is the distance to Proxima Centauri, measured in light years. And when we say it like that, 4.24 light years, it has a kind of comfortable abstractness to it. A small number, something that fits neatly on a page. That doesn't alarm you. That sounds almost manageable. But let us translate it into something the human body can feel. A light year is the distance light travels in a single year. Light, the fastest thing in the known universe, moves at approximately 300,000 kilometers every second. In 1 second, it could circle the Earth 7.5 times. In 8 minutes, it reaches the sun from where you are sitting right now. In 4.24 years, it reaches Proxima Centauri. That distance in kilometers is approximately 40 trillion, 40 followed by 12 zeros. If you were to drive to Proxima Centauri in a car, traveling at highway speed, without stopping day and night, without ever pausing, the journey would take you approximately 50 million years. The dinosaurs went extinct 66 million years ago. You would have time to watch that happen, then continue driving and still not arrive. If you walked, it would take longer than the current age of the universe. And Proxima Centauri is our nearest neighbor, the very closest star to our sun. Beyond it lie hundreds of billions more, spread across a galaxy 100,000 light years wide, inside a universe containing at least 2 trillion galaxies. The scale is not just large. It is, in a very precise sense, incomprehensible to the human nervous system. We are not built to feel these distances. Our brains evolved on the African savanna, measuring space in the lengths of a day's walk. We perceive depth to maybe a few kilometers with our eyes. Beyond that, everything blurs into the abstraction we call far away. But the universe does not care about our perceptual limits. It is exactly as large as it is. And here's where the story really begins. Not with the distances themselves, but with the fact that we are apparently the first species on this planet to look up at those distances and say, we are going to figure out how to cross them anyway. That is not a small thing. In the entirety of Earth's 4.5 billion year history, countless species have looked at the sky. Birds navigate by stars. Whales use magnetic fields that trace the geometry of the planet. But no species before us, as far as we know, has built instruments to measure the distance to those stars, derived the physics of space-time, and then sat down with paper and pencil and engineering budgets and asked, how do we get there? We're doing that now, with real physics, real proposals, real money. Two of those proposals stand above the rest in terms of scientific seriousness, not because they are certain to work, but because they are rooted in principles we have actually confirmed in laboratories and observatories. They represent two genuinely different answers to the same terrible question: how do you cross 40 trillion kilometers? One answer is to ride something that already crosses that distance constantly, effortlessly, at the speed of light, a beam of photons, a wave of pure energy. You build a sail, you catch the light, you let the universe push you. The other answer is to refuse the distance entirely, to fold space around yourself, to compress the universe in front and stretch it behind, and to arrive not because you travel fast, but because you made the journey shorter. A sail and a warp bubble, a whisper and a revolution. We will spend the next 2 hours understanding both: the physics, the history, the engineering, the philosophy. And by the end, you will have a clearer sense of which of these roads, if either, leads to the moment when a human being, or at least a human-made object, sets down on a world orbiting another star. But first, we need to understand why the problem is as hard as it is. Because the barrier is not simply distance. Distance, after all, is just a number. The barrier is physics. There is a natural human impulse, when confronted with a very large distance, to assume that the solution is simply a faster version of what already exists. We crossed oceans with ships, then faster ships, then eventually airplanes. We reached the moon with rockets, and so the thought follows, surely, with bigger rockets, better fuel, more thrust, we could simply go further. This impulse is understandable. It is also, when applied to interstellar distances, almost entirely wrong. And understanding why it is wrong is perhaps the most important single step in appreciating what solar sails and warp drives are actually trying to solve. The problem begins with a piece of mathematics derived by Konstantin Tsiolkovsky in 1903, a Russian schoolteacher working in the town of Kaluga, who spent his evenings developing the theoretical foundations of rocketry decades before the first liquid-fueled rocket flew. His rocket equation is elegant and devastating in equal measure. It states, in essence, that the amount of propellant a rocket must carry grows exponentially with the velocity it wishes to achieve. Not linearly, exponentially. Double your desired speed, and you don't need twice the fuel. You need vastly more than that, because the fuel needed to accelerate the earlier fuel must also be carried and burned. The equation folds back on itself in a kind of cruel mathematical recursion. For travel within our solar system, this is manageable, challenging, expensive, but manageable. We have reached Mars. We have sent probes to Jupiter, Saturn, Uranus, Neptune, and beyond. These missions operate in a range of tens of kilometers per second. Chemical rockets, ion drives, and gravitational slingshots can handle this. But interstellar travel is not just further in the solar system sense. It requires a fundamentally different velocity regime. Consider Voyager 1, which has traveled further from Earth than any human-made object, moves at approximately 17 kilometers per second. This is extraordinary by human standards. It is roughly 50 times faster than a commercial airplane. And at that speed, the journey to Proxima Centauri would take approximately 73,000 years. To make a mission to the nearest star civilization ally meaningful, meaning it returns data within a human lifetime, or at least within a few generations, you need to travel at somewhere between 1 and 20% of the speed of light. The faster end of that range, 20% of light speed, would get you to Proxima Centauri in just over 20 years. The slower end, 1%, would take over 400 years, long by human timescales, but at least within the span of a civilization's institutional memory. Let's take a modest target, 5% of light speed. That is approximately 15,000 kilometers per second. Compared to Voyager's 17 kilometers per second, that is nearly 1,000 times faster. Now apply the rocket equation. To accelerate a spacecraft carrying even a modest payload, say a few hundred kilograms, to 5% of light speed using chemical propellant. You would need a quantity of fuel that staggers calculation. Not a large rocket, not a very large rocket, a massive propellant that would exceed the mass of the observable universe many times over. This is not an engineering problem. It is a categorical impossibility. Chemical rockets, no matter how refined, no matter how well engineered, cannot solve the interstellar distance problem. They are the wrong tool, not insufficiently powerful, but wrong in kind. Like try to empty an ocean with a teaspoon, and concluding that what you need is a slightly bigger teaspoon. Even nuclear propulsion, which we will discuss, while dramatically more energetic than chemical combustion, runs into the same exponential wall at the velocities required for a meaningful interstellar mission. This is why solar sails and warp drives are interesting, not because they are exotic or futuristic, but because they're the only serious concepts that escape the tyranny of the rocket equation. The solar sail escapes it by carrying no propellant at all. A sail doesn't push against anything it carries. It pushes against something that is already everywhere. Photons, the particles of light streaming outward from every star. There is no propellant mass to account for. The equation's cruel recursion simply does not apply. The warp drive escapes it in a different and far more radical way, by not moving the ship at all, in the conventional sense. If space-time itself is what carries you, then you are not a rocket accelerating through space. You are a bubble of space being carried, like a leaf on a river. The rocket equation, which describes how objects accelerate through space-time, becomes irrelevant if you are moving the space-time itself. Both approaches are genuinely clever responses to a genuinely brutal constraint, but they are not equally developed, not equally understood, and not equally close to realization. We will come to all of that in time. But before we reach the present, we need to honor the past. Because the story of interstellar propulsion is not a story that began yesterday. It is a decades-long, beautifully serious scientific tradition built by some of the most rigorous and imaginative minds in the history of aerospace. And their work, even where it failed, left behind ideas that still echo in every current proposal. There is something quietly moving about the history of interstellar propulsion studies. These were not the projects of dreamers who ignored the laws of physics. They were, almost without exception, the work of serious engineers and physicists who understood the laws of physics precisely and set about finding every possible loophole within them. The story begins, as many aerospace stories do, in the mid-20th century, at the intersection of nuclear physics and the space race. The year is 1958. The first artificial satellite, Sputnik, has been in orbit for less than a year. The space age is newborn, and in a small project operating under the code name Orion, a group of American physicists, including Ted Taylor, one of the most gifted nuclear weapon designers of his generation, and the mathematician Freeman Dyson, whose name you may already know, began seriously examining a seemingly absurd idea. What if you could power a spacecraft by detonating nuclear bombs behind it? Not metaphorically, literally. A spacecraft equipped with a massive pusher plate, a thick disk of metal at its base, would release small nuclear devices behind it at regular intervals. The explosions would push against the plate, accelerating the ship. Each detonation would be like a controlled, directional nuclear pulse. On paper, and increasingly in engineering detail, Project Orion worked. Dyson's calculations showed that a large Orion-class vehicle could potentially reach Mars in weeks rather than months. More ambitiously, an interstellar variant, a ship of truly enormous scale, perhaps millions of tons, could potentially reach nearby stars within a century, traveling at a few percent of light speed. The physics was not speculative. Nuclear explosions are well understood. The engineering was extreme, but not categorically impossible. And for a few years in the late 1950s and early 1960s, Orion was a real program with real funding and real test flights, using conventional explosives as stand-ins for the eventual nuclear charges. Then came the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Orion was canceled, Dyson later described this as one of the great missed opportunities in the history of space exploration. Not because Orion was certain to work at interstellar scale, but because it was the one propulsion concept of that era that was unambiguously grounded in tested physics. The dream did not die with the program. It transformed. 15 years later, in 1973, the British Interplanetary Society, a venerable institution founded in 1933 that has long served as a home for serious, rigorous futurism, launched Project Daedalus. Over 5 years, a volunteer team of engineers and physicists produced what remains one of the most detailed engineering studies of an interstellar vehicle ever completed. Daedalus was designed to reach Barnard's star, approximately 6 light-years away, within 50 years of launch. The propulsion concept was inertial confinement fusion. Small pellets of deuterium and helium, 3 would be compressed and ignited by electron beams, producing fusion microexplosions at a rate of 250 per second. The exhaust velocity of fusion drive is orders of magnitude higher than chemical propulsion and significantly higher than even nuclear fission. The numbers worked. Daedalus could, in theory, reach 12% of the speed of light. But Daedalus had 2 fatal constraints that the study acknowledged with admirable honesty. The first was helium-3, the preferred fusion fuel, which is extraordinarily rare on Earth, but thought to exist in abundance in the atmosphere of Jupiter. Mining Jupiter's atmosphere was a required prerequisite for building Daedalus. The second was deceleration. Daedalus had none. It was a flyby mission. It would pass through the Barnard star system at 12% of light speed, conducting observations for a few days, and then continue on into the interstellar void. It could never stop. It could never land. These limitations were not hidden. The Daedalus team stated them plainly. The study was an exercise in understanding what was physically achievable at the frontier of known engineering, not a proposal to build the ship next Tuesday. Project Longshot followed in 1987. Developed by students and faculty at the U.S. Naval Academy and NASA, it revisited many of Daedalus' concepts for a mission to Alpha Centauri. Like Daedalus, Longshot was a flyby mission. Like Daedalus, it required fusion propulsion not yet demonstrated at any scale. It added a nuclear fission reactor for onboard power, and it solved some of the communication challenges Daedalus had glossed over. It was, again, serious work, and again, it was a study, not a program. Then something interesting happened in the early 21st century. The conversation about interstellar travel shifted from government-adjacent study groups to the world of private initiative. In April 2016, the Breakthrough Starshot initiative was announced by the Israeli-Russian entrepreneur Yuri Milner, with the theoretical physicist Stephen Hawking as a public face, and the physicist and laser expert Philip Lubin of the University of California, Santa Barbara, as a key scientific advisor. Starshot proposed something radically different from all its predecessors. Not a large, crude, or complex autonomous spacecraft, but a fleet of tiny probes, each the size and mass of a postage stamp, accelerated to 20% of light speed by a ground-based laser array. At 20% of light speed, the probes, dubbed Starships, would reach the Alpha Centauri system in approximately 20 years. They would carry miniaturized cameras, sensors, and communication systems. They would transmit their data home over the 4.24 light-year journey. Breakthrough Starshot was not a dream or a thought experiment. It came with $100 million of initial funding, a team of serious scientists, and a research roadmap. The physics, laser propulsion of light sails, is based on real, demonstrated principles. But it also came with genuine and significant engineering challenges that the team has always acknowledged openly. The laser array required, roughly 100 gigawatts of coherent, steerable laser power, is approximately 10,000 times more powerful than the most powerful laser systems currently in existence. The sail must survive being illuminated by that power for the minutes of acceleration without vaporizing. The Starships must survive the interstellar medium, the thin but non-zero sea of gas, dust, and cosmic radiation that fills the space between stars, while traveling at a fifth the speed of light, where even a collision with a single hydrogen atom carries significant energy. And there is still no solution to the deceleration problem, The probes would race through the Alpha Centauri system in hours. As of 2025 and 2026, breakthrough Starshot remains in an active research and development phase. Prototype laser sail technologies have been tested. The physics of the concept continues to be refined. It has not been abandoned, but neither has it solved all of its foundation challenges. What Orion, Daedalus, Longshot, and Starshot share, despite spanning nearly 7 decades and wildly different technological approaches, is a quality of intellectual honesty that is genuinely admirable. Each project engaged seriously with the hardest parts of its own proposal. Each acknowledged its limitations. Each left behind a body of knowledge that the next generation of researchers build upon. They are a lineage, a tradition, and it is within that tradition that solar sails and warp drives must now be understood. We have now arrived at the heart of things. Throughout all of this history, through Orion's nuclear pulses and Daedalus fusion microexplosions and Starshot's laser beams, a pair of fundamentally different ideas has persisted. Two approaches that are not simply different engineering solutions, but different philosophical commitments about how a civilization should relate to the universe it wishes to cross. Let us name them properly, and then let us sit with them for a moment before we begin to analyze them technically. The first is the solar sail, or in its most advanced form, the laser sail. In its essence, this technology says the following: the universe already provides what we need. Light is everywhere. Photons, the most abundant form of energy in the cosmos. They travel at the maximum speed permitted by physics, and when they strike a surface, they impart momentum. A sail does not fight the universe. It does not carry explosive propellants or demand that we discover fusion on an engineering schedule. It asks only that we build a surface thin enough and large enough to catch the light that is already flowing freely from every star. There is something almost philosophical, almost humble in this approach. The sail does not conquer the cosmos. It flows with it. It is the interstellar equivalent of catching the wind. The second is the warp drive. Specifically, the class of spacetime geometries first described mathematically by the Mexican physicist Miguel Alcubierre in 1994. This technology says something entirely different. The universe's rules as they stand are not adequate for what we wish to do, so we will change the local conditions of the universe. General relativity tells us that space-time is not a fixed, rigid stage on which events play out. It is a dynamic, malleable medium that can be curved, compressed, and stretched by the presence of mass and energy. A warp drive proposes to exploit this malleability deliberately, to engineer a bubble of space-time, inside which passengers sit in comfort, while space itself rushes them toward their destination at whatever effective speed is desired. The warp drive does not humble itself before the universe. It does not flow. It bends. These are not just technical distinctions. They reflect something deep about two different human instincts, two different stories we tell ourselves about our relationship with nature. One story says, nature is our home, and we should learn to live within it gracefully. The other says, nature is our raw material, and sufficient intelligence can reshape it to our purposes. Both instincts have served us. We are a species that learned to swim with ocean currents, and also a species that built canals where no rivers ran. We learned to read the wind, and also to build engines that made the wind irrelevant. The same duality lives in these two technologies. But philosophy, however illuminating, does not make a spacecraft. Physics does. Engineering does. And when we subject both of these approaches to the rigorous scrutiny of 21st century science, what do we actually find? We find something more interesting than a simple verdict. We find two technologies at vastly different stages of development, with vastly different relationships to experimental reality, but also with unexpected complementarity. They are not rivals competing for the same mission. They may, if either is ever realized, serve entirely different purposes. One the emissary of data, the other the carrier of people. One near-term and narrow, the other long-term and transformative. One already tested in space, the other still living in the mathematics of general relativity. And we find beneath both of them the same ancient human imperative that built the ships that crossed the Pacific and the rockets that left the atmosphere. The refusal to accept that somewhere is unreachable. In the chapters that follow, we will go deep into each of these technologies. We will examine the physics with care, what is confirmed, what is contested, and what remains genuinely unknown. We will trace the engineering challenges not to frighten or discourage, but to understand honestly what each path actually requires. We will visit the laboratories and the equations and the observatories where these ideas are being tested and refined right now, in the 2020s, as you listen to these words. And then, in the final movement of this journey, we will ask the question that underlies everything. What kind of civilization do we need to become to make either of these real? What does it cost? Not in money, but in time, in transformation, in the willingness to think across centuries rather than quarters. The distance to the stars has not changed. 40 trillion kilometers sits between us and even the nearest sun. But the space between an impossible idea and a realized one is not measured in kilometers. It is measured in the slow, patient accumulation of understanding, equation by equation, experiment by experiment, generation by generation. We have already begun. There is a moment in the history of every great idea when it crosses from metaphor into mathematics. For the solar sail, that moment happened not in a laboratory or a workshop, but in a letter. In 1608, the astronomer Johannes Kepler, the man who derived the laws of planetary motion, who gave us the elegant mathematics of how worlds orbit their suns, wrote to his friend and correspondent Galileo Galilei. He had been watching comets. Specifically, he had noticed something that puzzled him. Comet tails always point away from the sun, regardless of the direction the comet is traveling. A comet approaching the sun has its tail streaming behind it. A comet departing the sun has its tail streaming ahead of it. As if being pushed, Kepler concluded correctly that something from the sun must be pushing those tails. He called it a solar breeze, and in his letter to Galileo, he wrote words that have become famous in the history of spaceflight. Given ships or sails adapted to the breezes of heaven, there will be those who will not shrink from even that vast expanse. It would take 3 centuries for the physics to catch up to Kepler's intuition. In 1862, James Clerk Maxwell, the Scottish physicist whose equations unified electricity and magnetism and laid the foundation for all of modern electromagnetic theory, demonstrated mathematically that light carries momentum. This was not obvious. Light has no mass. It weighs nothing on a scale. And yet Maxwell's equation showed unambiguously that when light strikes a surface, it exerts a pressure, a tiny pressure, almost unimaginably small by everyday standards, but a real, measurable physical force. This prediction was confirmed experimentally in 1900 by the Russian physicist Pyotr Lebedev, who built an extraordinarily delicate apparatus, a series of thin vanes suspended in a near-perfect vacuum, and demonstrated that a beam of light could visibly deflect them. The pressure was real. The force was real. Light pushed. The implications for space travel were first articulated seriously by Konstantin Tsiolkovsky, the same man whose rocket equation we discussed earlier, and by the German-Russian engineer Friedrich Zander in the 1920s. They noted that in the vacuum of space, where there is no air resistance to oppose it, even the tiny pressure of sunlight could, given enough time and enough sail area, accelerate a spacecraft to significant velocities. The idea was elegant precisely because it was free. No fuel, no combustion, no propellant to carry and exhaust. Just surface area, a sail, and the inexhaustible river of photons streaming outward from the sun at the speed of light. For decades, the solar sail remained a theoretical concept, beautiful but untested. Then gradually it began to fly. The first mission to intentionally use solar radiation pressure for attitude control was Japan's Icaro spacecraft, interplanetary kitecraft accelerated by radiation of the sun, launched in May 2010 by the Japan Aerospace Exploration Agency, JAXA. Icaros was a remarkable engineering achievement, a square sail 14 meters on each side, made of a polyamide film just 7.5 micrometers thick, roughly 1/10 the thickness of human hair. with thin-film solar cells embedded in the cell material itself to generate onboard power. It was deployed by spinning the spacecraft, using centrifugal force to unfurl the sail in deep space. Icaros worked. It demonstrated, in the actual environment of interplanetary space, that a solar sail could be deployed successfully, that it could generate measurable thrust from sunlight, and that the pressure of that sunlight could be used to steer the spacecraft. JAXA confirmed a solar radiation pressure force of approximately 1.12 millinewtons on the sail, a number that sounds negligibly small and in everyday terms is. But in the frictionless vacuum of space, even 1 millinewton of continuous force, applied over weeks and months and years, accumulates into meaningful velocity change. In 2019, the Planetary Society, a non-profit space advocacy organization founded by Carl Sagan, among others, launched LightSail 2, a CubeSat-based solar sail mission in low Earth orbit. LightSail 2 carried a 32-square-meter sail made of mylar, and it successfully demonstrated that a solar sail could raise its own orbit using sunlight alone, an important milestone because orbital raising is precisely the kind of maneuver that matters for eventually escaping Earth's gravity entirely. Then, in April 2024, NASA launched the Advanced Composite Solar Sail System, known as ACS-3, a technology demonstration mission designed to test new lightweight composite boom structures for deploying large sails. Earlier boom materials were heavy and prone to structural problems in the thermal cycling of space. ACS-3 used carbon fiber composite booms, lighter, stronger, and more dimensionally stable, as a pathfinder for future, larger sail missions. Each of these missions represents genuine, incremental, hard-won engineering progress. The solar sail is not a concept. It is a demonstrated technology with a flight heritage. It has been to space. It has worked. But here is where honesty demands that we introduce some perspective. These missions, remarkable as they are, operated in the inner solar system, close to the sun, where sunlight is still relatively intense. They carried small payloads. They achieved accelerations that, while real, are still modest by interstellar standards. A standard solar sail driven purely by sunlight from our sun faces a fundamental problem. Sunlight gets weaker with distance. The intensity of solar radiation falls off with a square of the distance from the sun. By the time you reach the orbit of Jupiter, sunlight is already 25 times weaker than at Earth's distance. By the time you reach the edge of the solar system, the heliopause, where Voyager 1 now travels, it is tens of thousands of times weaker. A pure solar sail, pushed only by sunlight from our sun, can achieve high velocities if it starts close to the sun, dipping into the inner solar system on a close perihelion pass to maximize the sunlight intensity, then deploying the sail. Researchers like Corin Bale-Jones and others have calculated that a sail performing a close solar pass, coming within the orbit of Mercury or even closer, could potentially achieve escape velocities of several hundred kilometers per second, compared to Voyager 17. That is a genuine improvement. A mission to Proxima Centauri at that speed would still take tens of thousands of years rather than 73,000, but the principle scales in the right direction. For truly interstellar timescales that matter to human civilization, decades rather than millennia, the pure solar sail is almost certainly insufficient on its own, which is precisely where the next chapter of the story begins. Because what if we didn't rely on the sun? What if we built our own? The leap from solar sail to laser sail is, conceptually, a simple one. A solar sail is pushed by the photons streaming naturally from a star. A laser sail is pushed by the photons from a laser, a coherent, directed, enormously powerful beam of light that we aim at the sail from a fixed point, typically somewhere in or near Earth orbit or on the lunar surface. The advantage is enormous and immediate. A laser beam does not spread out and weaken with distance the way sunlight does, or rather, it spreads far more slowly. A well-collimated laser beam can maintain its intensity over much larger distances than solar radiation. And critically, we can make a laser as powerful as our energy budget and engineering allow. The sun gives us what it gives us. A laser we control. The physics of laser sailing was studied seriously beginning in the 1960s, but the concept received its most rigorous and systematic modern development through the work of Philip Lubin, a physicist at the University of California, Santa Barbara. Lubin's research program, which he calls DE-STAR, Directed Energy System for Targeting of Asteroids and Exploration, developed the theoretical and engineering foundations for using phased laser arrays in space. The core idea is to build a large array of individual laser emitters that act coherently together. Not a single enormous laser, but thousands or millions of smaller units whose beams are precisely coordinated in phase, effectively functioning as one beam of extraordinary power. Lubin's calculations, published in peer-reviewed journals and NASA technical reports beginning around 2015, showed that a laser array of sufficient scale. He envisioned arrays ranging from tens of meters to tens of kilometers on a side, could accelerate small probes to a substantial fraction of the speed of light. The key insight was that the probe had to be very small. The smaller the probe, the less mass it has, and the more easily radiation pressure can accelerate it. This is the foundation upon which breakthrough Starshot was built when it was announced in April 2016. The Starshot concept is specific and detailed enough to describe with precision. The probes, called starships, will be gram-scale spacecraft, roughly the size of a postage stamp, integrating cameras, communication lasers, navigation systems, and power sources on a single chip using miniaturized electronics technologies that were already emerging from Moore's Law by the mid-2010s. Each star chip will be attached to a sail, a few meters across, made of an extremely thin reflective material, and a combined probe plus sail system would have a total mass of perhaps a few grams. The laser array, sometimes called the laser cannon in popular descriptions, though the technical term is phased laser array, would be ground-based or possibly space-based, with a total output power on the order of 100 gigawatts. To put that in perspective, the entire electrical generating capacity of the United States is approximately 1,000 gigawatts. The Starshot laser array would require roughly 10% of that capacity, concentrated into a single beam and fired for a few minutes at each departing probe. During those minutes of illumination, the star chip will be accelerated at thousands of times the force of Earth's gravity, an acceleration regime that would kill any human passenger instantly, but that a gram-scale electronic chip, carefully engineered, might survive. By the end of the acceleration phase, the probe will be traveling at approximately 20% of the speed of light. At that velocity, the journey to Alpha Centauri, 4.37 light-years away, slightly farther than Proxima Centauri, would take approximately 21 years. The data from the flyby would take another 4+ years to travel back to Earth at the speed of light. So roughly 25 years after launch, humanity could receive the first close-up observations of another stellar system, within the lifetime of the scientists who designed the mission, within the political memory of the civilization that funds it. This is why breakthrough Starshot captured imaginations so effectively when it was announced. It was not proposing travel to the stars within a generation. It was proposing information from the stars within a generation. Data, images, measurements, not a colony, not an expedition, but the first touch of human technological senses on another sun's domain. The funding was real. $100 million was committed for initial research. The Scientific Advisory Committee included serious, credentialed researchers, and the underlying physics, radiation pressure from a laser acting on a reflective sail, is not speculative. It is demonstrated. But there's always a but in honest science. The engineering challenges of breakthrough Starshot are significant, and the project's own scientists have stated them clearly in published research and public communications. It is worth walking to the most important ones, because they illustrate something important about the difference between a sound physical principle and a functioning spacecraft. The laser array, 100 gigawatts of coherent laser power, phase-locked across an array that must maintain beam quality, what engineers call coherence, over the minutes of the acceleration burn. Current high-power laser systems achieve gigawatts of peak power for fractions of a second in laboratory settings, or kilowatts of continuous power in industrial or defense applications. getting from kilowatts to 100 gigawatts. Sustained, phase-locked, and precisely steerable is not an incremental engineering step. It requires advances in power generation, thermal management, and adaptive optics that are real areas of active research, but that do not yet have clear timelines. The sail material. During the acceleration phase, the sail must reflect nearly all of the laser light striking it. If it absorbs even a fraction of % of 100 gigawatts, it will be vaporized in seconds. Current reflective materials can achieve very high reflectivities, but the margins required for Starshot are at the edge of what materials science has demonstrated. Researchers, including Harry Atwater at Caltech, have worked on photonic crystal sail materials that might achieve the necessary reflectivity, and progress has been made. But the problem is not solved. The interstellar medium. Space is not empty. Between the stars, there is a thin haze of hydrogen atoms, dust grains, and other particles. The interstellar medium. At everyday spacecraft velocities, this medium is essentially irrelevant. At 20% of light speed, it is not. Each hydrogen atom encountered by the star chip carries significant relative kinetic energy. Over the years of the journey, cumulative erosion of the sail and the chip's surface could be significant. Researchers have proposed protective coatings and geometric designs to minimize this erosion, but the problem requires further study to quantify precisely. Communication. A gram-scale chip for light years from Earth, attempting to transmit data home with a laser powered by its tiny onboard power source. The signal-to-noise challenges are formidable. Lubin and colleagues have done detailed analyses suggesting it is feasible, but it requires a sensitive receiver array on the Earth end. And deceleration. Perhaps the most philosophically uncomfortable constraint. There is no way to slow down. The star chips would race through the Alpha Centauri system in a matter of hours. They cannot stop. They cannot orbit. They cannot land. They are witnesses, not settlers. Flybys can teach us an enormous amount. The New Horizons flyby of Pluto in 2015 revealed a world of astonishing complexity in data collected over just a few hours, but they are fundamentally limited in what they can know. As of 2025 and 2026, Breakthrough Starshot continues its research program. Laboratory experiments on laser sail interactions have been conducted. Materials science research on sail substrates continues. The project has not announced a launch date, nor has it completed the engineering demonstration of the core laser acceleration concept. It remains what its team honestly describes as a research and development phase, working toward the proof-of-concept experiments that would precede any full-scale mission. This is not a criticism. This is precisely the right place to be, given the scope of what is being attempted. Rome was not built in a day, and neither, it seems, will the first interstellar probe. The solar and laser sail path, then, is this: a technology with deep experimental roots, genuine flight heritage, a sound physical foundation, a credible if enormously challenging near-term interstellar application in Starshot, and a clear developmental trajectory, even if that trajectory is measured in decades rather than years. Now we turn to the other road, and here, the landscape changes dramatically. To understand the warp drive, you need to understand something about the nature of space itself. Not space as an empty container, a void through which objects travel, but space as a physical medium with properties that can change. This is one of the most profound shifts in the history of human thought, and it came from Albert Einstein. Before Einstein, space was what Isaac Newton said it was: absolute, fixed, and featureless. A perfect, invisible stage on which the drama of the universe played out. Objects moved through space. But space itself did not do anything. It simply was. Einstein's general theory of relativity, published in 1915, replaced this picture with something far stranger and far richer. In general relativity, space and time are not separate things. They are woven together into a single four-dimensional fabric called spacetime. And this fabric is not rigid. It is dynamic. It curves in the presence of mass and energy. A massive object, a planet, a star, a black hole, bends spacetime around itself, and other objects moving through that curved spacetime follow the bends, which is what we experience as gravity. This is not a metaphor. Space-time curvature has been measured to extraordinary precision. The GPS satellites in orbit around Earth must account for the curvature of space-time caused by Earth's mass, or their clocks would drift and navigation would fail within hours. Gravitational waves, ripples in space-time itself, predicted by Einstein and first directly detected in 2015 by the LIGO Observatory, carry energy and travel at the speed of light across billions of light years. Space-time is real, physical, and malleable. Now, general relativity also contains one of the most cited limits in all of physics. Nothing with mass can travel through space-time faster than light. The speed of light in a vacuum, approximately 300,000 kilometers per second, is a universal speed limit. As an object with mass accelerates, it requires more and more energy to continue accelerating, and the energy required approaches infinity as the speed approaches light. You cannot reach light speed if you have mass. This seems to close the door on faster-than-light travel absolutely and permanently. But, and this is the crucial insight that makes the warp drive theoretically interesting, general relativity places a speed limit on objects moving through space-time. It says nothing about the speed at which space-time itself can change. And observations of the early universe suggest that space-time can move, expand, or contract at rates far exceeding light speed. The inflation and expansion of the universe in its first moments is believed to have occurred faster than light, because it was space expanding, not objects moving through space. Miguel Alcubierre, a Mexican theoretical physicist, then a graduate student at the University of Wales in Cardiff, recognized this loophole in 1994 and published what has become one of the most famous papers in theoretical physics, The Warp Drive, Hyperfast Travel Within General Relativity, in the journal Classical and Quantum Gravity. Alcubierre's proposal was mathematically specific. He described a particular geometry of space-time, a solution to Einstein's field equations, in which a bubble-flat space-time is surrounded by a region where space is being contracted in front of the bubble and expanded behind it. The ship sits inside the flat bubble, experiencing no acceleration, no time dilation relative to the outside universe, and no violation of local physics. But the bubble as a whole moves through space faster than light, because it is the space itself that is moving, not the ship through space. The elegance of the Alcubierre metric is genuine. It satisfies Einstein's equations. It does not require the ship to locally exceed the speed of light. Passengers inside the bubble would experience normal physics. They would feel no g-forces. They would not be crushed by acceleration. In principle, a ship using an Alcubierre drive could travel between stars in days or hours of ship time and arrive at the destination having aged only those days or hours. This is not science fiction grafted onto real physics. It is a real mathematically valid solution to Einstein's field equations. It is, in that narrow sense, allowed by the laws of physics as we understand them. But here, the but is significant. The Alcubierre metric comes with a set of physical requirements that are, under current understanding of physics, either deeply problematic or outright impossible. The most fundamental is a requirement for what physicists call exotic matter, specifically matter with negative energy density, to generate the space-time curvature that the Alcubierre metric describes, to compress space in front and expand it behind. The geometry requires a region of space where the energy density is less than zero, not just very low, actually measurably physically negative. Ordinary matter, every atom, every particle, every form of energy we know about in everyday life, has positive energy density. It curves space-time in one direction, inward toward itself, like a weight pressing down on a rubber sheet. To curve space-time in the opposite direction, to push space outward, to expand it, you need something that curves space-time the other way, something with negative energy density. Does such a thing exist? The honest answer is, maybe in a very limited sense, but nothing like what Alcubierre's metric requires. There is a real quantum mechanical phenomenon called the Casimir effect, in which two uncharged, parallel metal plates placed very close together in a vacuum experience a tiny attractive force. This force arises because the vacuum between the plates, the quantum vacuum, which is not truly empty but seized with quantum fluctuations, has slightly less energy than a vacuum outside the plates, where a wider range of quantum fluctuation modes are permitted. In this very narrow, very specific context, a region of space can have a slightly negative energy density relative to the surrounding vacuum. Alcubierre and subsequent researchers pointed to the Casimir effect as a proof of principle that negative energy densities are not forbidden by physics. And in that very limited sense, they are correct. But the quantity of negative energy required by the original Alcubierre metric is staggering. Initial estimates placed it in the range of the mass-energy equivalent of a planet the size of Jupiter in negative energy. The entire mass of Jupiter, expressed not as positive energy but as negative. No known physical process produces negative energy at anything remotely approaching this scale. Subsequent theoretical work, including contributions from Harold Sonny White at NASA's Johnson Space Center in the early 2010s, proposed modifications to the bubble geometry, oscillating the bubble thickness, for example, that could mathematically reduce the required exotic energy by many orders of magnitude. White's proposals generated significant media attention and some internal NASA support for a small research program. But these calculations were contested within the theoretical physics community. Critics pointed out that the mathematical manipulations involved certain assumptions and approximations that were not fully justified, and that independent replication of the energy reduction results produced inconsistent findings. White's work remains a minority position in the field, and should be understood as a speculative hypothesis rather than a confirmed theoretical advance. What is not in dispute is that the Alcubierre metric requires exotic matter of some kind. What is deeply uncertain is whether physically realizable exotic matter exists in forms and quantities that could actually be harnessed. But exotic matter is not the only problem. The Alcubierre warp bubble has several other theoretical pathologies that emerge from subsequent analysis. There is a control problem. The interior of the warp bubble is causally disconnected from its walls. Light from inside the bubble cannot reach the bubble's leading edge because the bubble is moving faster than light. This means that a passenger inside the bubble cannot send signals to the bubble's drive mechanism. You cannot steer. You cannot turn off the drive from inside. The bubble, once created, must be programmed to stop at a predetermined destination. The implications for navigation are severe. There is the quantum stability problem. Stephen Hawking and others showed that the quantum vacuum near the event horizon-like surfaces of the warp bubble would likely generate intense radiation, analogous to Hawking radiation, that would destabilize the bubble or potentially kill its passengers. There's the time travel problem. Physicists including Alan Everett showed that a sufficiently advanced civilization with multiple warp-capable ships could, in principle, use Alcubierre drives to create closed time-like curves, paths through space-time that loop back to their own past, enabling time travel. Many physicists believe this indicates a fundamental flaw in the concept, since most interpretations of physics suggest that true time travel to the past leads to contradictions. And there is, underlying all of this, a more basic epistemological problem. We do not have a complete theory of quantum gravity, general relativity, and quantum mechanics. The two most successful physical theories ever devised are mutually inconsistent at the extreme conditions relevant to warp drive physics. A full understanding of what is and is not possible with space-time geometry may require physics we do not yet possess. It is important, when discussing the warp drive, to be scrupulous about the difference between theoretical exploration and experimental progress, because the media history of this topic has not always maintained that distinction with care. Let us be precise about what has happened in this field in recent years. In 2021, two significant theoretical papers appeared that advanced the conversation in substantive ways. The first was published by Alexei Bobrick and Johnny Martiri in the journal Classical and Quantum Gravity, a rigorous, peer-reviewed venue. Bobrick and Martiri conducted what amounts to a systematic classification of warp-drive spacetimes, a taxonomy of all possible geometries that could achieve warp-like effects. Their key finding was that some subclasses of warp metrics, not the original Alcubierre metric, but related spacetime geometries, might be achievable using matter with non-negative energy density, meaning matter that does not violate known energy conditions in physics. This sounds like a breakthrough, and in a narrow theoretical sense it represents genuine progress. But it is essential to understand what Bobrick and Martiri actually showed and what they did not. The geometries they identified that avoid exotic matter still require matter to be arranged in configurations of extraordinary precision and at densities that have no plausible engineering pathway. They demonstrated that exotic matter is not universally required for warp-adjacent spacetimes, not that building a warp drive is feasible or even approachable with known physics. The paper is honest about this in its conclusions. The second 2021 paper was by Eric Lentz, published in Classical and Quantum Gravity, proposing a warp drive solution based on what he called solitons, self-reinforcing wave structures in the space-time metric. Lentz argued that his soliton-based geometry could be achieved without exotic matter, using conventional positive energy matter distributions. This paper attracted significant attention and was widely reported in science media. However, subsequent analysis by other theoretical physicists raised questions about the energy requirements of Lentz's solutions, finding them to be extremely large even if technically positive, and questioning whether the matter distributions required could be physically realized. The peer response to Lentz's work has been cautiously interested but not confirmatory. It remains an active area of theoretical debate. Also in this period, the company Applied Physics, a private research organization that positions itself at the interface of theoretical and applied physics, published work on what they called positive energy warp drives, attempting to develop practical frameworks for warp propulsion based on geometries that do not require exotic matter. Applied Physics has been unusually effective at communicating this research to general audiences. Their work is real, conducted by credentialed researchers, and published in legitimate venues. But independent assessments from the broader theoretical physics community have consistently noted that the achievable effective speeds of the applied physics warp geometries, when their energy requirements are constrained to physically reasonable values, fall well short of what would be needed for interstellar travel. The gap between the mathematical object and a functioning drive remains enormous. What does not exist as of 2025 and 2026 is any experimental pathway for warp drive research. There is no laboratory experiment, no tabletop demonstration, no observational data that connects warp drive theory to physical reality in the way that the Casimir effect connects to quantum field theory, or that Ikaros connects laser sail theory to spaceflight. The warp drive is entirely a mathematical object, an object whose mathematics is real, valid, and worth studying, but an object that has not yet touched the world of experiment in any form. This does not make it valueless. Theoretical physics has often preceded experiment by decades. General relativity was published in 1915. The first direct detection of gravitational waves, predicted by the theory, came in 2015, 100 years later. The theoretical work on warp drive geometries is genuinely advancing our understanding of the solution space of Einstein's equations, and that is worth doing. But intellectual honesty requires that we state clearly what we do not know. We do not know if exotic matter exists in the forms required. We do not know if the quantum mechanical effects near the bubble walls would be survivable. We do not know if the causality problem can be resolved. We do not have a theory of quantum gravity that would allow us to fully analyze the relevant extreme conditions. And we have no experimental program capable of testing any of these questions in the foreseeable future. The warp drive, as of today, is the most intellectually exciting and most physically uncertain of all interstellar propulsion concepts. It is simultaneously the most transformative. If it worked, it would change everything about what humanity can do in the cosmos, and the least ready. We have now spent considerable time with both roads. Let us stand at the fork and look carefully at each of them. I want to resist the temptation to declare a winner. The question of which technology will truly make us an interstellar species is not a contest with a simple answer. It is a question about timescales, purposes, and what we mean by interstellar. Let us instead compare them across 6 dimensions, carefully and without advocacy. Physics readiness. The solar and laser sail rests on confirmed physical principles. Radiation pressure is measured. Photon momentum transfer is understood from first principles and experimentally verified. The Alcubierre warp drive rests on a valid mathematical solution to Einstein's equations, but requires either exotic matter whose physical existence is unconfirmed or matter configurations of extraordinary and perhaps unachievable precision. On physics readiness, the sail leads by a wide margin. Engineering pathway. Solar sail technology has been demonstrated in space. Icaros flew. Light Sail 2 flew. ACS-3 flew. There is a clear, if enormously challenging engineering development path from current technology to a breakthrough Starshot-type mission. It requires advances in laser power, sail materials, and miniaturized electronics, all of which are active fields of engineering research with measurable progress. Warp drive technology has no engineering pathway. There is no engineering laboratory working on warp bubble generation. There is no experimental setup that produces even a nanoscopic spacetime curvature for propulsion purposes. The engineering gap for warp drives is not large. It is essentially infinite from the current position. This is not a permanent verdict. It is a current state of affairs. Timeline to first mission. Breakthrough Starshot's own researchers have spoken of a developmental timeline on the order of decades, perhaps 20 to 30 years to proof of concept, longer to a full mission. That is long by human individual standards, but short by civilizational ones. A warp drive propelled mission has no credible timeline. It is not possible to give a date, even approximately, when the physics and engineering barriers will be overcome, because it is not known if they can be overcome at all. Scalability. This is where the comparison becomes more nuanced. A Starshot probe is gram scale. It carries no crew. It cannot decelerate. It is an information-gathering instrument, extraordinarily valuable, but limited in what it can do at the destination. Scaling laser sail technology to a crewed mission faces challenges that are not merely quantitative, but qualitative. The laser array required to accelerate a human-carrying spacecraft will be orders of magnitude more powerful than anything Starshot envisions. And a deceleration problem. There is no laser array at Alpha Centauri to slow you down. Remains unsolved for crewed missions. The warp drive, if it ever worked, would in principle be scalable to any size of spacecraft, would permit deceleration and maneuvering, and would allow round trips within human lifetimes. Its potential ceiling is vastly higher than the sails. Its floor, the minimum required to make it work at all, is also vastly higher and may not be achievable. Philosophical cost. The laser sail requires enormous civilizational engineering, a ground-based or orbital laser array drawing power comparable to a substantial fraction of current global electricity generation. It is a significant but comprehensible infrastructure project of the same category as large particle accelerators or space telescopes, only vastly bigger. The warp drive requires either the discovery and controlled production of exotic matter with properties not observed in nature, or the manipulation of space-time geometry at scales and precisions far beyond anything in current physics. The philosophical cost of the sail is investment. The philosophical cost of the warp drive may be something more like a revolution in our understanding of reality. Civilizational purpose. This is perhaps the most important dimension. A Starshot probe can send us data about another stellar system within a human lifetime. That is genuinely extraordinary. It would be among the greatest scientific events in human history. But it cannot send people. It cannot begin a settlement. It cannot make us, in the deepest sense of the phrase, an interstellar species, beings who live and reproduce and build civilizations beyond our own solar system. A warp drive could, in principle, do all of that. It could make interstellar travel as routine as intercontinental flight has become. The sail offers us eyes at the stars. The warp drive offers us presence among them. And so the honest answer to the question this video poses, which technology will truly make us an interstellar species? Maybe that the sail is the answer to a smaller but real and achievable version of that question, and the warp drive is the answer to the full, uncompromised version, but that the full version may be further away than any living person can reliably predict. They are not rivals. They are milestones on the same road, separated by an unknown distance. The sail is the first step we can actually see from where we stand. The warp drive is a destination we cannot yet make out clearly, but whose possibility is written faintly in the equations of general relativity, waiting for a civilization wise and powerful enough to read it fully. There is a question that sits beneath all the physics and all the engineering, quieter than the equations, less visible than the diagrams of war geometries and sail deployments, but perhaps more fundamental than any of them. It is this: what kind of civilization does any of this actually require? Not what kind of spaceship, not what kind of laser array or sail material or exotic matter source. What kind of civilization? What kind of species? What kind of relationship with time, with energy, with our own future must humanity develop before the stars become genuinely reachable? The Soviet astronomer Nikolai Kardashev thought carefully about this question in 1964. He was attempting to develop a framework for thinking about the potential energy signatures of extraterrestrial civilizations. Try and understand what signatures a sufficiently advanced civilization might leave in the radio spectrum. In doing so, he proposed a classification scheme that has since become one of the most referenced frameworks in all of astrobiology and futurism. Kardashev suggested that civilizations could be classified by their total energy consumption. Not their technology, not their biology, not their culture, but the raw physical quantity of energy they control and use. A Type 1 civilization, in Kardashev's original framework, is one that has mastered the total energy available on its home planet. All the sunlight falling on that planet's surface, all its wind and geothermal and oceanic energy, controlled and usable at will. The number associated with Type 1 is approximately 10 to the power of 16 watts. 10 million billion watts of continuous power, every joule that the planet receives from its star, flowing through the civilization systems. A Type 2 civilization has mastered the total energy output of its star, not the fraction that strikes one planet, but the entire stellar luminosity captured and directed. The Dyson sphere is the most frequently cited embodiment of this idea, a structure of whatever form that surrounds a star and collects its light. The energy available to a Type 2 civilization is on the order of 4 times 10 to the 26 watts. It is a number that requires effort to even hold in the mind. A Type 3 civilization has mastered the energy of its entire galaxy. Now, where does humanity sit on the scale today? We currently consume energy at approximately 2 times 10 to the 13th watts. Our total global energy consumption, every power plant, every engine, every light burning in every city on Earth at this moment, amounts to about 20 terawatts. Continuous, year over year. A Type 1 civilization requires 1,000 times more than that. We are, by Kardashev's reckoning, not yet a Type 1 civilization. We are perhaps a Type 0.73 civilization, by the physicist Michio Kaku's interpolated estimate. A species that has unified its communications and begun to globally distribute its information and energy systems, but that has not yet fully harnessed even the resources of its own planet. Why does this matter for interstellar travel? Because when we look honestly at the energy requirements of the technologies we've been discussing, we find that they map almost cleanly onto the Kardashev scale. Breakthrough Starshot's proposed laser array, 100 gigawatts, 10 to the 11th watts, is approximately 100 billion watts. That is not yet at the Type 1 threshold, but it represents a serious fraction of our current global energy budget dedicated to a single piece of infrastructure. Getting there requires that we have become an energy civilization of substantial maturity, that we have solved the global energy transition, that we have developed the ability to concentrate and direct enormous power for sustained scientific purposes. It requires something like a peaceful, technologically coherent global civilization, which is itself not guaranteed. For laser sails, in other words, a mature, stable, globally unified civilization approaching, but not yet at Type 1, is probably the minimum prerequisite. For warp drives, the energy requirements, however uncertain, are almost certainly at Type 2 or beyond. The Alcubierre metric's original energy requirements approach the equivalent of a planetary mass in exotic energy. Even the most optimistic revised estimates, contested though they are within the theoretical community, require energy densities and configurations that no Type 1 civilization could plausibly achieve. A warp drive, if it is ever built, will be built by beings who have mastered their star, perhaps by beings who have mastered far more than that. This is not a reason for despair. It is a reframing. The distance to the stars is not only measured in light years. It is also measured in watts, in joules per second, in the long, generational project of building a civilization that is energetically mature enough to make the physics real. And there is something quietly hopeful in recognizing this, because energy is not fundamentally mysterious. We understand it. We can generate it from fusion, a technology that has been in development for decades, and that has, in recent years in facilities like the National Ignition Facility in California and Commonwealth Fusion Systems Spark Project, passed genuine milestones. We can generate it from sunlight at scale. We can generate it from the careful engineering of larger and larger systems over longer and longer timescales. The road to Type 1 is not hidden. It is the road we are already on. We are simply, by cosmic standards, very near the beginning. But energy is not the only prerequisite. There is something subtler required as well, something that has less to do with what's and more to do with institutional memory, with the ability of a civilization to sustain a project across not years, not decades, but centuries and generations. The Apollo program took a decade. The Hoover Dam took 5 years. The pyramids at Giza took roughly 20 years. The great cathedrals of medieval Europe took centuries, so long that the original architects would never see the spire, the builders' great-grandchildren sometimes completing what the founders had only begun, and yet the cathedrals were finished. Across hundreds of years, across wars and plagues and political upheavals, the project persisted. Something about the shared meaning of the project was transmitted generation to generation, not just in documents, but in culture, in identity. A warp drive may require the cathedral model of civilization, a project so large, so multi-generational, so culturally embedded that it outlives every individual who contributes to it, and is completed by people who were not yet born when it began. We have, as a species, done this before. We built the knowledge infrastructure that made modern physics possible across centuries of accumulated scholarship. The mathematics of general relativity that makes the warp drive theoretically interesting was built on foundations laid by Euclid, refined by Gauss and Riemann, extended by Minkowski, and completed by Einstein across more than 2,000 years of mathematical tradition, each thinker inheriting and building upon what came before. What we need to become is not mysterious. We need to become more than we are, energetically, institutionally, and in the depth of the time horizons we are willing to hold. We need to become, in the fullest sense of the word, a civilizational species, rather than merely a planetary one. The sail may be built by the civilization we are on our way to becoming. The warp drive may be built by the civilization that species eventually becomes. Looking back across millennia at us the way we look back at the first humans who shaped a tool from flint. And perhaps that is not a discouraging thought at all, because every civilization we know started somewhere small and looked somewhere vast and began the long walk toward it anyway. Let us set aside for a moment the question of which propulsion system we choose and sit with a different question, one that is less often discussed, but that may turn out to be just as fundamental. Who goes? Or perhaps more precisely, does anyone go at all? There are two philosophically distinct visions of interstellar travel, and they lead to very different places. In the first vision, we send machines, probes, robotic explorers, artificial intelligences, instruments without biology, without fear, without the need for food or oxygen or sleep, crossing the interstellar dark as pure information-gathering devices. In the second vision, we send people. We send the warm, breathing, dreaming, complicated fact of human biology across 4 light years of vacuum. Both visions are serious. Both have advocates, and they produce very different sets of problems. A breakthrough Starshot probe does not worry about radiation. It does not need to eat. It does not develop psychological disorders from years of isolation, or suffer the grief of watching its home star recede until it's indistinguishable from the other lights in the sky. A gram-scale electronic chip, carefully shielded and hardened, is far more durable in the interstellar environment than a human body. And in an age of increasingly powerful artificial intelligence, the scientific data a probe can gather and transmit home may be more comprehensive, in some respects, than what a human crew could observe and record. But a probe cannot decide to stay. It cannot look at an alien shoreline and choose to land. It cannot make the judgment calls that biology alone enables, the intuitive, embodied assessments of whether a world smells of life, whether the soil crumbles the right way, whether something unseen is moving at the edge of the instrument's range. And a probe, however sophisticated, carries no seed of continuation. If it is lost, it is simply lost. There is no one there to mourn it, or to adapt, or to find another way. Crude, interstellar travel is a different matter entirely. It is a matter of biology meeting physics, and the meeting is not a comfortable one. Begin with radiation. The interstellar medium, the thin sea of gas and plasma between the stars, is not truly empty. It carries galactic cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated to near light speed by supernova remnants and other energetic astronomical events. These particles do not respect spacecraft hulls. They penetrate most conventional shielding materials with relative ease, interacting with hull atoms and generating secondary radiation in the process, sometimes producing showers of secondary particles that are themselves damaging. On Earth, we are protected by two layers of shielding that space travelers will be without: the planet's magnetic field, which deflects a significant fraction of incoming cosmic ray particles, and the atmosphere, which provides equivalent of many meters of water in radiation shielding depth. In low Earth orbit, astronauts receive roughly 10 to 20 times the annual radiation dose of a person on the ground. On the lunar surface, the dose is higher still. On a voyage to Mars, higher again. And on an interstellar journey, lasting decades, in the open interstellar medium beyond the heliosphere's protective bubble, the doses accumulate into territory that current biology cannot comfortably survive without either significant shielding, biological modification, or both. There is a problem specific to the fast sail scenario that deserves particular attention. What some researchers have called a hydrogen wall problem, or more precisely, the problem of relativistic hydrogen atom impacts. At 20% of the speed of light, each hydrogen atom in the interstellar medium, and there are on average about one atom per cubic centimeter in the average interstellar environment, arrives at the spacecraft with kinetic energy equivalent to a small particle accelerator collision. The cumulative dose of radiation produced by these impacts over 20 years of travel could, by some estimates, be severe. Research into this problem by William Edelstein and others has suggested that a thin layer of hydrogen-rich shielding at the bow of the spacecraft might be effective, but detailed calculations of the optimal solution remain an active area of study. Then there is the question of air, water, food, and the cycling of matter through a closed ecological system for decades. The concept of a closed ecological life support system, sometimes abbreviated CLSS in the aerospace literature, is the attempt to create, within the confines of a spacecraft, a self-sustaining loop of biological and chemical processes that recycles air and water, grows food, processes waste, and maintains the biological prerequisites for human survival indefinitely, or at least the duration of the voyage. This is not a fictional concept. The International Space Station runs partial versions of such systems. Researchers at institutions, including NASA's Ames Research Center and the European Space Agency, have spent decades developing and testing components of closed-loop life support. But sustaining a closed ecosystem reliably for 20, 50, or 200 years, long enough for a crewed interstellar voyage, is a challenge of qualitatively different magnitude than maintaining one for the 6-month tours typical of ISS residents today. Every biological and mechanical component must function, or be reparable, across time spans that dwarf all of human spaceflight history so far. The margin for catastrophic failure is zero, because rescue is not available. The nearest repair depot would be measured in light years. And then there is the deepest question of all. The one that is not an engineering problem, but an ethical one. What if the journey takes longer than a human lifetime? A laser sail mission to Proxima Centauri at a few percent of light speed, not Starshot's 20%, but a more modest crewed vessel, could easily require a century or more. No individual who boards that ship will arrive. The people who arrive will be the grandchildren or great-grandchildren of the people who departed. They will have been born aboard the ship. They will have known no other world. And they will arrive at a destination that was chosen not by them, not by their parents, but by ancestors who are by then long dead. This is a generation ship problem, and it is not simply a logistical one. It is a profound question about consent and identity, and what we owe to people we have brought into existence. The children and grandchildren born on a generation ship did not choose the voyage. They did not sign up for the mission. They were created by the decisions of the original crew in an environment specifically constructed to serve that mission, and then they were born into circumstances that gave them no alternative. They cannot exit. They cannot return. They are, in a sense, conscripted into an interstellar project by the very fact of their birth. Philosophers and ethicists have grappled with this question with increasing seriousness as the plausibility of generation ships has grown in the scientific conversation. The philosopher Cameron Smith at Portland State University has written extensively on the population genetics and social structures that a viable generation ship crew would require. Others, including Konrad Sosik, have examined the psychological and ethical dimensions of multi-generational space habitats. There are no easy answers. The analogy is sometimes made to the children of immigrants, people who did not choose to leave their homeland, who were carried by their parents' decision to cross an ocean, and who must make sense of an identity that spans two worlds. But the interstellar equivalent is more extreme. There is no way back, no homeland that the children can visit, no dual citizenship available. These are not problems that physics or engineering can solve. They are problems that we, as a species, will have to think our way through. They require the development of ethical frameworks adequate to genuinely unprecedented situations. And developing those frameworks is part of what it means to become a civilization capable of going to the stars. The honest answer to the people problem is that we do not yet have all the solutions. In biology, in engineering, in ethics, or in the structures of human psychology that will determine whether a crew of 50 or 500 can maintain coherent social order across a century of interstellar isolation. But the questions are being asked, the research is being done, the frameworks are being built, and perhaps that is the right thing to notice, that every era in the history of exploration began with people who did not have all the answers and went anyway, not recklessly, thoughtfully, with as much preparation as the knowledge of the time permitted. But they went. There is a particular kind of intellectual danger that comes with any large, dramatic framing. When we organize a conversation around two competing visions, sail and warp drive, patience and revolution, physics as it is and physics as it might be, we risk creating a false binary. We risk forgetting that there are other roads of forest, quieter roads, less photogenic roads, roads without the philosophical grandeur of folded spacetime or the elegant poetry of a sail catching the light of distant suns. This chapter is for those roads. It is a chapter about epistemic humility, about the recognition that the history of science is full of moments when the most likely seeming path was overtaken by something unexpected, something that had been sitting quietly in equations all along, waiting for the right moment to be taken seriously. Begin with Project Daedalus' legacy, nuclear pulse propulsion, and its more refined successor, inertial confinement fusion propulsion. The core idea, as we discuss in the history chapter, has been with us since the 1950s. Daedalus envisioned small pellets of deuterium and helium, three ignited at a rate of 250 per second, producing a continuous stream of fusion microexplosions that would push the spacecraft from behind. The exhaust velocity of a fusion drive, the speed at which the propellant leaves the engine, is vastly higher than any chemical rocket and significantly higher than nuclear fission. The physics is sound. Fusion is the energy source that powers the stars, and we understand it in considerable theoretical detail. The challenge has always been practical. We have not yet demonstrated sustained net energy-producing fusion in a controlled setting, though recent milestones at the National Ignition Facility in California, where in December 2022, and in subsequent experiments in 2023 and 2024, the facility achieved fusion ignition, producing more energy from fusion than was delivered to the fuel by the laser, have narrowed the gap between theoretical possibility and practical reality considerably. Fusion propulsion is not fusion power generation. The engineering requirements are different in important ways, but the fundamental physics demonstration that controlled fusion ignition is achievable is a meaningful milestone. If controlled fusion propulsion were ever developed at sufficient scale, it could achieve exhaust velocities that translate to spacecraft velocities of several percent of light speed. A mission to Proxima Centauri at, say, 5% of the speed of light would take about 85 years. Long, but within the span of a generation ship's expected operational life. And unlike the laser sail, a fusion-drive spacecraft could, in principle, decelerate upon arrival. It carries a propellant with it, and it can burn that propellant in reverse. It can stop, it can orbit, it can explore. Fusion propulsion sits in an interesting middle space in the conceptual landscape of interstellar travel. Less exotic than warp drives, more capable than current technology, and resting on physics that is, in its fundamentals, confirmed, even if the engineering path to implementation remains long and uncertain. Then there is antimatter propulsion, which occupies the highest rung of what might be called physically plausible but practically staggering. Antimatter is real. Every particle of ordinary matter has a corresponding antiparticle of identical mass but opposite charge. When matter and antimatter meet, they annihilate each other completely, converting their entire combined mass to energy according to Einstein's famous equation. This is the most energy-dense reaction possible by the laws of physics as we know them. Gram for gram, matter-antimatter annihilation releases approximately 10 billion times more energy than chemical combustion and hundreds of times more than nuclear fission. A spacecraft with an antimatter propulsion system could, in principle, achieve exhaust velocities approaching the speed of light. The propellant efficiency will be incomparably higher than any other known option. A small quantity of antimatter fuel could, in theory, propel a spacecraft to tens of percent of light speed. But the practical barriers are severe enough to make antimatter propulsion, currently, more of a theoretical benchmark than an engineering roadmap. First, antimatter does not exist in nature in accessible quantities, as far as we can observe. The universe appears to be dominated by ordinary matter. One of the great unresolved mysteries of physics is why, since the Big Bang should produce matter and antimatter in equal quantities, and they should then have annihilated each other completely, leaving nothing. Something broke the symmetry and left us with the matter-dominated universe we inhabit. Antimatter does exist. It is produced in small quantities in high-energy particle accelerators, and it appears naturally in some radioactive decay processes, but producing it requires enormous energy inputs. At CERN, the world's leading particle physics facility, the production rate of antihydrogen is measured in atoms per hour to atoms per minute. The quantity of antimatter produced by all human efforts in history, combined, amounts to nanograms, billionths of a gram. The quantity required to power an interstellar spacecraft would be on the order of tens to hundreds of grams at minimum, and realistically far more. The gap between current production capability and the required scale is many orders of magnitude. Closing that gap would require either a revolution in antimatter production physics or the Type II civilization energy budget that puts us back in Kardashev territory. Second, antimatter must be stored without touching ordinary matter, which means suspending it in magnetic or electrostatic traps with near-perfect reliability for years or decades. The trap technology exists in principle, but not at the scales required. There are also quieter, less discussed candidates on the propulsion menu that deserve at least a brief acknowledgement. Magnetic sails, sometimes called mag sails, are a concept proposed in 1990 by Robert Zubrin, better known as the founder of the Mars Society, and David Andrews. A mag sail does not use light pressure at all. Instead, It generates a large magnetic field around the spacecraft using a superconducting loop of wire. This magnetic field interacts with the solar wind, the stream of charged particles, mostly protons and electrons, flowing outward from the sun at several hundred kilometers per second. The magnetic field deflects these particles, and their momentum transfer pushes the spacecraft. A mag sail accelerates more slowly than a laser sail, but requires no external infrastructure, no laser array, no ground station. It carries its own driver with it. More relevantly, a mag sail can also be used for deceleration in the target star system. If the destination star has its own stellar wind, and virtually all stars do, the spacecraft arriving at high velocity could deploy its mag sail and use the target star's own outflow to slow down. This is an elegant solution to the deceleration problem that plagues most interstellar mission designs, and it has received serious analysis in the peer-reviewed literature, including work by Zubrin himself and subsequent researchers. The limitations of mag sails are their acceleration rates. They are slow, suitable perhaps for 1% light speed missions over very long timescales. But their deceleration capability makes them potentially valuable as part of a hybrid mission architecture, used in concert with a laser sail for the outbound acceleration phase. Laser thermal propulsion is another quieter candidate. Rather than pushing on physical sail, a laser from a remote facility heats a propellant carried by the spacecraft, which then expands and exits through a nozzle in conventional rocket fashion. The advantage is that the propellant can be a lightweight gas, the heating can be very efficient, and the system avoids the structural challenges of deploying a large reflective sail in space. Some researchers have proposed laser thermal propulsion as a near-term path to solar system escape velocities, as a stepping stone toward more ambitious interstellar applications. None of these alternatives is, on its own, likely to be the technology that first crosses the interstellar distance. But they matter for two reasons. First, they remind us that the solution to interstellar travel may be composite, a hybrid architecture that uses one propulsion system to accelerate, another to cruise, and yet another to decelerate. The history of complex engineering projects is not typically the history of single technologies. It is the history of systems. The aircraft that first crossed the Atlantic was not a single innovation, but a synthesis of 100 previous innovations in engines, airframes, navigation, fuel, and human training. Second, they embody something important about the scientific process itself. The value of maintaining many parallel lines of inquiry, of not overcommitting to the most dramatic or most publicly visible idea at the expense of quieter, but perhaps ultimately more tractable approaches. Science advances not only through the brilliant, paradigm-shattering insight, but through the patient, incremental work of people who are not trying to revolutionize everything at once, who are simply trying to solve the next problem in front of them. The next problem in front of us is significant enough. Go outside tonight if you can. Find a place where the city's light retreats a little, a park, a hilltop, a field at the edge of town. Wait for your eyes to adjust. Let the darkness fill in around you, the way it always does, slowly, the stars appearing one by one as your pupils open to receive them. Now find the brightest thing in the southern sky, or wherever Alpha Centauri rises from your latitude. If you are in the northern hemisphere, it may not be visible, lost below the horizon, but you know it is there. You have always known it is there. A faint point of light, unresolved to the naked eye, indistinguishable from 10,000 others unless you know exactly where to look. That point of light is a star. Actually, it is 3 stars, a bound system, orbiting one another in a slow gravitational waltz that will continue for billions of years. One of them, Proxima Centauri, has a planet, a rocky planet, in a habitable zone, where liquid water might pool in low places, where temperatures might, in some seasons, feel familiar to the body that you carry with you. The light from that star that is entering your eyes right now, this very moment, as you stand there in the cooling air, left its source 4 years and 2 months ago. You are not seeing the star as it is. You are seeing it as it was. Every act of looking at the night sky is an act of archaeology. The further you look, the older the light, the light from the Andromeda Galaxy, faintly visible to the naked eye as a smudge in the constellation of the same name, is more than 2 million years old. The human species did not yet exist when that light began its journey toward your eyes. This is a strange thing to sit with. We are bathed every night in information that is older than we are, light that has traveled for longer than our civilization, longer than our species, sometimes longer than our planet, and that delivers itself quietly to our eyes, carrying news, a universe that may have changed substantially since those photons were emitted. And we are, as far as we know, the only beings in the history of this planet who have understood this, who have traced the geometry of it, who have worked out from first principles that light travels at a finite speed, that distance and time are equivalent in a certain profound sense, that when you look outward, you look backward. Birds feel the stars. Whales trace magnetic fields that map the planet's interior. But only we have looked at that faint point of light and said, I know what you are. I know how far away you are. I know how long ago that light left you. And I'm going to figure out how to send something across that distance to visit you in person. That is not a small thing. It may be the most extraordinary thing about us. We are the first species on this planet, and possibly one of the first species in a very large region of this galaxy, to have developed the capacity to ask these questions with equations rather than just with wonder, to have moved from mythology to mathematics, from stories about the stars to missions toward them, from Kepler's intuition about solar breezes to Alcubierre's warp bubble solutions, from the earliest speculative sketches in a scientist's notebook to prototype laser sails deployed in the actual void. There is something worth naming in that trajectory, something that can get lost in the daily friction of scientific disagreement and engineering setback and the slow grind of institutional funding and political will. The trajectory exists. It has direction. And its direction is unmistakably outward. Think about the timescales involved in what has been accomplished and what has been understood in a remarkably short period. 66 years separate the Wright brothers' first power flight at Kitty Hawk in 1903 from the moment Neil Armstrong stepped onto the surface of the moon in 1969. 66 years from a wooden aircraft that flew 12 seconds over a sand dune to a human being standing on another world. The entire sweep of powered flight, from its first fumbling moments to its interplanetary expression, happened within a single human lifetime. We are now in the early decades of a second such arc, not of flight, but of starflight, of the long, patient, generational project of understanding what the physics actually permits and building toward it with everything we have. The first solar sail flew in 2010, the first serious, funded, peer-reviewed proposal for a mission to another stellar system using demonstrated physical principles emerged in 2016. The first fusion ignition experiments confirmed that the fuel source for interstellar propulsion is achievable in a controlled setting. The theoretical work on warp geometries, however far from realization, has become a legitimate subfield of general relativity research with papers in respectable journals and sessions at serious conferences. None of this adds up yet to a starship. It does not add up to anything you could board and ride to Proxima Centauri. It is the equivalent, perhaps, of the decade before Kitty Hawk, when the Wrights were still reading about bird flight and building bicycles and running wind tunnel tests and accumulating, piece by piece, the understanding that would eventually make 12 seconds of power flight possible. We are in that decade. We are, cosmically speaking, just before the moment when the runway ends and the wheels leave the ground. And there is something else to consider as we close. We tend to think of interstellar communication as something that lies ahead of us, a future capability, something we will do once we have the technology. But the universe has been communicating with us, in a certain sense, for as long as we have existed. Every photon that reaches a human eye from beyond our solar system is a message, carrying information about its source. The spectral lines in starlight tell us the chemical composition of stars. The Doppler shift in those lines tells us the velocity of approach or recession. The polarization of light from distant galaxies tells us about magnetic field structures on cosmological scales. The cosmic microwave background radiation, the the afterglow of the Big Bang itself, detectable by instruments as a uniform radio is permeating the sky, is the oldest message in existence, a letter from the universe's infancy, written in the language of quantum fluctuations, telling us about the geometry and composition and origin of everything. We have learned to read these messages. Not all of them. We are still learning, still developing new instruments and new techniques and new theoretical frameworks that allow us to extract more information from the light that falls on us without cease. But we are reading, we are answering, in our way, broadcasting radio waves, sending out Voyager's golden records, reflecting laser light off the moon, and measuring the return. We are participants in a cosmic conversation whose scale we are only beginning to appreciate. What we have not yet done is go. We have received messages. We have sent messages. We have not yet physically crossed the distance. But consider every tool, every concept, every piece of mathematics that we would need to begin seriously attempting that crossing now exists in some form. The physics of radiation pressure is understood and demonstrated. The mathematics of space-time geometry is mature and detailed. The engineering of closed life support systems is progressing. The miniaturization of electronics has already produced devices of remarkable capability in gram-scale packages. The energy sources that would be required, fusion, large-scale solar, perhaps eventually others we have not yet anticipated, are subject of active, funded research programs with measurable progress. The raw materials are here. What remains is time, and a particular kind of civilizational patience that allows a species to stay committed to a project across decades and centuries through the disruptions and upheavals and redirections that history inevitably brings. It may comfort you, as you sit with the scale of this, to remember that the universe itself is patient. The star whose light you are watching tonight has been shining for billions of years and will shine for billions more. It is in no hurry. It will be there when we arrive. And the distance, the 40 trillion kilometers, the 4.24 light years, the number that seemed at the beginning of this journey, so intimidating that it bordered on paralyzing, is real and it is vast and will require genuine, perhaps unprecedented civilizational effort to cross. But it has a value that can be written down. It is finite, it is a number, and numbers can, in principle, be crossed. There's a phrase that the philosopher and mathematician Blaise Pascal wrote in his Pensées in the 17th century, in a passage reflecting on the terror of infinite spaces. He wrote the silence of those infinite spaces and how it frightened him. The sky in his time was magnificent and incomprehensible and closed, a theater of lights with no backstage, no way through, no door into the dark between the stars. We have found the door. We are mapping the hallway. We do not yet know how long the hallway is, exactly, or what we will need to build to traverse it fully. But the mapping has begun. The physics is real. The equations are written. And somewhere in the long river of human time, not in the life of anyone listening to these words tonight, but in the life of the civilization that we and our children and our children's children are building generation by generation, something of ours will leave the solar system with intention, not adrift, like Voyager, tumbling in the dark with its clock stopped and its cameras long since turned off, but aimed, purposeful, heading toward a light that someone once decided was worth reaching. That is the horizon we are building toward, not a destination that exists independently of us, waiting passively to be found. A horizon that we are, by the act of imagining and working and asking and building, constructing ahead of ourselves as we walk toward it. The stars are very far away. We are going anyway. The light from Proxima Centauri is still traveling towards you. It has been traveling for 4 years to reach your eyes tonight. And somewhere in the long patience of that journey, in the photons crossing the void, in the equations solved by people who will never see their completion, in the sails that may one day open like enormous silver flowers in the dark between the suns, something that is unmistakably human is already, in some sense, on its way.